Good afternoon. I'm Bob Morris from Research and Development. It's my pleasure to introduce Nathan Schubkegel. Nathan's a senior in computer science from Washington State University, and for the last year he's been working on a senior design project with SEL. It's kind of a unique senior design project. A lot of them are usually only a semester long. This one's a full year, and the first part of the project they worked on specifications and design and planning, and the second part actually did the implementation. So a lot of senior projects we just kind of jump in and go do some design, but this one really teaches the discipline of software development process, which is really important to us at Schweitzer Engineering. Also, Levi's, interesting name for the software package. It's not a pair of blue jeans. Levi's is load encroachment visualization, and why is that important to us? Load encroachment's a capability we designed into, I think the first product was the 321 about 17 years ago, and it's a patented technology that really allows our distance and directional relays to outperform the competition. And you've probably heard load encroachment a lot over the years and not really understood what it was. And today we're going to get to see what it looks like, which is really what's so cool about Nathan's project. Nathan worked with Kurt Gerchens and Jeff McDougall and others in the automation group, and his instructors, Jack Hagemeister at WSU, that I know many of you know as well. So with that, I'll turn it over to Nathan.
Thank you. Let's see. Hey there. I'm Nathan Schubkegel. Marvin Ojwang was my partner, but he's not able to be here today, so I'll be giving this presentation alone. I better look at this. The PC Software 1 department is the one where you can see I've got a badge. I'm an intern. I actually got this as a result of this senior design project, and I'm very thankful. Today I'm going to present the requirements and needs that the project needed to satisfy, as well as its success and why it's cool, why it's actually going to be used in the future. It's going to be neat. But first, load encroachment is a technique implemented by SEL relays. It's a collection of 6 settings that enable the relay to distinguish between, well, semi-intelligent distinguish between ground faults and a quick load change. Both of these events, the ground fault there is a power line on the ground, and quick load change, heavy industrial equipment, or I don't know, if everyone in the house turned on the vacuum cleaner at once, you'd have something that looks like a load encroachment happening, but only one of those has to cause a trip. This is what the graph looks like. You might have seen this a couple weeks ago when that nice guy presented the patent information. You got a graph with 4 circles there. Those are zones, and a forward load region and a reverse load region. These areas outside the circles, when a point lies outside those circles, it's not a fault. And when a point lies inside these circles, it's a fault, and each zone registers a different behavior when that fault occurs. So while load encroachment is great, because that little intersecting region is also not a fault, even though it's inside the circles, and that's what you get by using load encroachment. So when you get a point in this graph coming from the relay registers its value, it will drift over time, and it, that's what happens. When it gets out of that intersecting area, into the circles, it becomes a fault. And setting up these settings is the challenge of load encroachment. This is what users normally have. This is a screenshot from AcSELerator QuickSet, the 5030 software. On the left are these gray boxes that they all represent a group of settings. So there's tons of them. And this particular one, load encroachment, has 6 settings. And how many of you think you could set up the load encroachment graph right now? We got a power engineers, all right. Well, with this, you can. This is not a screenshot, it's just a doctored image, but it is just as good as the real thing because, because what users will do is they'll click and drag these items and to change the values in here, or they will manipulate the values in the text boxes, and the graph will update to represent what they've changed. Let me give you a demo. Now, this is our running prototype. When you move the mouse over things, they highlight, and when you click them, they drag. What you might see here over by my mouse is this number changing all the time. This is pretty cool. And so the shape of the graph changes. You go in there, you see that yellow interaction point? That was cool. It's good to hear that. Somebody said, sweet. And so it's beautiful. It works at This is cool. It automatically resizes, and so this will give you an idea of what we had to create. It's neat to show you the finished product before I actually explain the challenges that we had. Usability is the biggest one. Jeff and Kurt were really good about being happy with what we made for them. You know, unless it was desperately wrong, they liked it. It was great, but it was a common course of events to see us go through and document a feature and design it, write out documents, and implement it, and find after construction that it's unusable. It's worthless because we just didn't have it in our hands to click and play with it. The classic example is deciding what a user should be allowed to click and drag. We decided that the user should be able to click and drag any shape, any part of the shape should highlight so that users can quickly find out what to click on. The alternative is, if any of you have used Microsoft Visio, they provide little boxes that you go over and click and drag to expand the shapes. And that's good, but fortunately we didn't need to do that. We can provide a more general solution. So this was pulled from our requirements documents. During a click and drag, the circle's edge will always touch the mouse point. So what that looks like is when you click and drag the circle, here's that red mouse point. I'll do it from here. You should click and drag, and it'll follow the mouse. The problem is if you click and drag down by this side of the circle, it grows exponentially large really quickly with not very much mouse movement. It's bad. That confuses users. So the solution is to limit the growth of the circle on one axis. See, click and drag from the bottom and goes up there. So does that make sense? Is that kind of cool? I have this dotted line, horizontal dotted line showing to illustrate to users that they should move, that's what they're moving, actually, that line, not the circle. And it just happens to kind of circle. The result, the side effect is that growing sideways is ignored. So if you clicked on this side of the circle and dragged, nothing would happen. Users figure it out pretty quickly, because when they see it's not moving, they kind of jerk the mouse around, and, oh, there it goes. So that's the solution. Another usability issue we ran into was that having the graph automatically resize and reorient to ensure that its contents remain visible. This seems intuitive, like the graph should always show what it's supposed to show. But it conflicts with having the user able to drag the mouse outside the bounds of the graph. Because what happens is when the user wants to drag, on the left we have how the mouse is going to behave, and on the right is what the user will see. And what you'll see is the user, everything needs to stay in the graph while the graph needs to change consistently and smoothly. So you're going to click and drag that way. On the left, it acts like it's growing outside the bounds of the control, but on the right, everything else shrinks to keep everything displayed. And this is what works. If you did it the opposite way, either users wouldn't be able to see this line, or users' mouse, they'd see the line and their mouse wouldn't be hooked up with it. This is the usable situation, the usable solution, because the graph resizes at a predictable and consistent speed. That's nice to see. Let me show you actually some of the alternatives. Here's a good example. These options down here are different behaviors that we experimented with before finding a good one. Here's no active resizing at all. If I click and drag this circle, it grows outside the bounds of control, and that's good. It's consistent and reliable, but it's not as good as it could be. This alternative, free active resizing entirely. I'm dragging this line around. This works, and everything is smooth and fluent, but what happens is the origin is moving. So when I get around here to this, near the ear, it kind of loses control, and that's no good. So finally, here's the perfect solution. Have it resize and keep the origin in the same position. It gets a little worrisome when you see the graph being small and it's not resizing again, but it's got that coming after feature. So actually, when people review this, when this goes out to market, I'll have some input on what management likes best. So I got to show you this picture again. This is novel. This is a novel project because this control here is written in C#, but it's used in a Delphi program. We have a Delphi prototype that looks like the one that I showed earlier. It's basically identical, got these same settings, and it works. And as soon as my mentors get a little more time, probably this summer, we'll get a version of this in QuickSet. It's going to look neat. This is also novel because some competitors can draw load encroachment, but we're the first ones to actually interact with it. I tried going online and Googling load encroachment, and I got some PDFs of research. I got one application that could actually draw it, but this is it. This is new. And that's the value of this project, is that it's actually going to be extended into the summer, hopefully. Levi's at the start of a library of SEL components that let users change settings graphically. It's referencing your design to actually be used. I heard a lot of stories of my partners, what do you call them, cohorts, who made a project and it was real fun, and then the company's going to throw it away. It's kind of sad. So this is cool. I'm happy for this to have value in my work. Last thing I want to tell you about is how we've actually designed it to be easy to extend. This is a picture of the Levi's architecture. This red box, where's my mouse there, represents the code we made that's specific to load encroachment. Each of these little boxes represents a piece of the graph. And this bottom right thing is the final content, final result. So you can pull this, you can pull this load encroachment arc unit out and put it in a new component, and it'll work just like it's supposed to, because we designed it that way. The other part of this is that we depend on a reusable framework. This is reusable because it has to be used to use our component. So about 29% of the code is in this framework that makes it easier for us to develop these components. 30% of the code is actually in Levi's itself, and 40% of our code were demos and test drivers. That's about 14,000 lines total, which isn't big. It's all right. Possible feature extensions. This is neat. I pulled these images out of a 321 relay manual, the ground distance characteristics control and the time over current characteristics control. I think it would be easy to make these if they have any value. I haven't asked any power engineers yet, but they would use this reusable framework and possibly some components from this diagram down here. Here's that expanded. If you dissect that image, you get a graph and that circle, that Mohs circle unit, and this, which hasn't been written yet. And that's the value. This is all that has to be written to implement something that controls like this. It's great. It's cool to be able to brag about that. That's kind of the epitome of software engineering. Make it reusable. So in summary, I gotta say that this is unique. Load encroachment hasn't been done visually interactive like this before. It's cool. It's successful because we've worked hard to make it quick to learn and easy to use. It's not just thrown together. We've gone through it a couple times. And it's valuable because I get to work on it this summer, and SEL relays will benefit from this. Customers will be able to set load encroachment more effectively. I actually have to thank Jeff McDougall, and Nathan Wood. He's the one who first gave us the introduction to load encroachment. These code review engineers gave us their time during the semester, and Jack Hagemeister, always the prophet of software engineering. You have any questions about this? Would you like to see the demo again? That's all right, I think you'll trust me. Thank you.
Nathan, thank you very much. A very impressive demonstration. And Nathan mentioned that there were only 14,000 lines of software in there, and just to put that in perspective, when I first started, that's how many lines of code were in an entire relay. So, so he says it's pretty trivial, but there's a lot that's going on behind the scenes there. And what's really cool about it is that it can eliminate a lot of setting errors. So I'm sure we'll definitely take advantage of all the work that Nathan's done. So congratulations, great job. So, and with that, it's Friday lunch. Enjoy your weekend.